Okay, let's get started. So today we are going to be doing parser combinators, and we are going to be turning assembly into machine code. And so the first thing that we need to do is, before we start parsing this stuff, we need to know how it's going to work. And this is a very, just like when we were working with the logic circuits and the ALU, this is a real assembly language that can do anything that any other assembly language can do, but it's also got a very restrictive syntax, which is going to help us for parsing and also mean that we can probably understand the spec and get to a place where we feel pretty good about it in just a bit. So this is what the source files that we're going to be looking at sort of look like. You're going to see lines that start with the @ sign and then a number, or @ sign and then like a variable or a symbol, and then some other ones that do computations, and there's going to be a few other things, but it's fairly simple. And I guess I should show you kind of what it looks like when we finish it as well. So what comes out is going to look like that. That's what comes in, and what comes out is going to look like this. And so this looks a lot more intimidating than the other one, right? It's this is a lot less friendly than the programming languages that we're used to, and far less friendly than Haskell for sure. But at least it's a little bit human parsable, right? Whereas this or this other one, after it's been transformed, starts to get really difficult. But the important thing to realize is there's actually a one-to-one for each of these languages. So for every line of our assembly, there's a line of machine code. And so that's going to make it easy. We're not going to have to take one line of assembly and turn it into 10 lines of machine code, which would be the case if we were using a higher order programming language, right? And essentially, I believe this is what separates assembly from the other more convenient languages, is that we've got this explicit relationship. So first thing we have to know about are that we have 3 registers which are going to reside on our CPU. And these are memory storage locations for 16 bits that are very easily accessible, and we can refer to them by these letters, A, D, and M. So then we also have, beyond that, we have instructions. We have 3 types of instructions that we can give our CPU. We have an A instruction, and an A instruction is going to start with an @ symbol, and it's going to be followed either by 16 bits, which is going to be an actual memory address, right? So if I wanted to target the first memory address, then I would say @ and then 15 zeros and then a 1. But we also can use symbolic addresses. And these are just like variables that we would have in programming languages that we're used to. And so, and some of these are predefined by the hardware, and some, or preloaded into the hardware, I should say, and some of them are user-defined by us. And so there is a symbolic address, R0, which corresponds to the 0 index, and there's R1, which corresponds to the first one. And so if I did @R01, that would be the same as @15 zeros 1. And this is going to be important because the way that we achieve iteration is by establishing a memory address and then calling a loop back to that memory address. And we can do that with 16 numbers, but the assembly is already hard enough to read, right? And so giving it a name like starting to add numbers now can help us keep track of where we are in our system. So there's C instructions and then loops. And okay, yeah, so here's the examples. And to get of the A instructions. And there's when we reference this in our assembly, it's going to do what it's going to do is it's actually going to take that and it's going to store the location of that address into the A register. And so if I reference @counter, the CPU is going to take the address for counter and then store that into the A register so that we can use it later on. And if it's a straight binary number, then it won't do any lookup. We won't need to do any lookup for what it refers to. It'll just store that number. And I guess I should clarify, I made an error there. It's not the CPU that does the resolution of the symbols. We will do that in our assembler. So by the time this makes it to just machine code, each one of these will be a @ which is indicated by a single bit being flipped or not. Lets us know if it's an @ an A instruction or not, followed by the explicit memory address. So here are our C instructions. So the C instructions are where we actually do our work. And these are composed of 3 different types. We have a destination, a computation, and a jump. And so of these 3 portions, only the computation is required, which is going to let us demonstrate some of the powers of these parser combinators, because we'll need to check to see if a destination is present, and then if it isn't, we'll need to check if a computation is present. If the computation is also not present, we'll need to throw a syntax error. But if return a syntax error. But if the computation is present, then we still need to check if a jump is present or not. And if the jump is present, we need to return it. But if the jump is invalid, then we need to return a syntax error. And so we only have 3 different registers that we have available to reference directly, A, D, and M. And then we have the computation can use any of the operators plus, minus, pipe, exclamation point, or and, along with the arguments for each of the registers plus a 1 or a 0. So my computation can be A plus D. It can be A or B. It can be A and B. It could be A plus 1. It could be 0. And so it could be exclamation, not A. It can be any combination of those. So then, finally, we have the jump. And what the jump does is the jump, if it evaluates to true, will look at what memory address is currently stored in the A register. And if it is true, it will jump to the A register. And so JMP denotes that we will jump no matter what. And then these other ones all indicate conditions. JEQ is if the computation is equal, then we will jump. Not equal, we will not jump. Less than 0, we'll jump. Greater than 0, we'll jump, etc. So these are some examples of how these things can play out. Computation only, setting the memory register to 0 there. We have it may not look like a computation because there's only a 0, right? But in reality, the computation is 0, which cannot resolve any further, and we store that in the D register. And then we have destiny, computation, and jump at the bottom, and only the computation without any destination in the one slightly above that. And actually, let's play this.
To separate?
Yeah, the semicolons are to separate the D, the C, and the J, the destination, the computation, and the jump. But they're only necessary if they're present. So if there's no destination, then you don't start with the semicolon. You just start with the computation, right? Otherwise, they're let's get back on track. Okay. Beyond this, we have some predefined symbols. or variables that we need to take into account. So the A, the D, and the M, we need to know what the addresses are for those registers. And we also need to know a few other things. There's R0 to 15, which are these are just conveniences for the first 0 to 15 registers. And the reason for this is that we're often going to have to store 16 bits. And so it's just easier to, instead of coming up with our own names, have that loaded in. A few other ones of note are this screen. So eventually, we're going to need to have a reference to every single pixel in our screen. And the way that we draw things on the screen is by actually sending a high voltage or a low voltage to that pixel. And so we need the screen map in memory. And also the way that we're going to get input from our keyboard is also very similar, where we're going to have a word that corresponds to each UTF-8 code. And I think that pretty much covers it. Let's go ahead and take a look at a simple hack assembly program and its corresponding machine code. So this is a program, and let's walk through. Let's see if actually together we can walk through and see what it does. So line 8, is this an address or a C instruction? Address. Anytime it starts with the @ sign, it's going to be address, and it'll either be a literal one, which means that it is a 16-bit binary, or it'll be a symbol. So this is an address, and it's also a symbol. It just doesn't have a very good human-readable name, right? It's just a 0. And so what happens at this point, anytime we come across a symbol, we need to go and look at every single address that is available and assign this symbol to be the nearest free address. So since this is the first symbol in our program, the only thing that currently exists is the map of preloaded symbols. So we need to walk through each of those and then find the next available one and assign it to this one. So even though it says 0, it's probably going to end up being something like memory register 16, right after the R15, or 17, or the 16th. Yeah, y'all are going to forgive me for that one. I can tell already. So then, what the second thing that does is it is going to store that into the A address, and it's going to store whatever the contents of that are into the M register. And then in line 9, it assigns that to the D. So then we follow and we do something pretty similar to the next one, and what we end up with is D minus M being stored in D. And then we store another symbol in our, we are going to map another symbol to a new memory address, and then it's going to check the jump greater than, which is going to compare the D and the M and jump only if the D is greater. And then it's going to run through a few other things, and at the end of this, what is happening is it is looking at the contents of two numbers that are stored previously in the registers for 0 and 1, and it's going to put the whichever one is greater in the register that is referenced with 2. Okay? And that corresponds to basically the same this once it's parsed into machine code. Okay, so let's go ahead and talk a little bit about how we're going to do this parsing. So in order to parse with we're going to have to first look a little bit into two type classes in Haskell, applicative and alternative. And this gets a little heavy for me, but I think that we're going to be okay. We've done some stuff with monoid. We've had Julie telling us a lot of cool stuff about functor, and we've looked at some of the laws and instances. So it's not going to be that. I think that we're going to be okay. We're all in this together. So we're going to need, with applicative, to provide an implementation of pure. And this is simply going to wrap up a value into an applicative. And we're also going to need to provide an instance of this function right here. And this function is going to take an applicative that contains a function and apply that function to the value that's held in a subsequent applicative. And Julie talked a little bit about this as well, but this is a way of allowing us to store both values and functions inside of our containers and still having a consistent API to deal with them. And then finally, in addition to those, for alternative, we're going to need to provide an instance for this operator. And this operator is going to be somewhat similar to the previous operator, except this operator is going to provide us the chance to succeed even if we're past a failing instance. So when we talked about functor with Julie, we talked about how the instance of functor, like let's say we have a maybe, right? It can be either a just value or a nothing. And if you ever get, let's say we have a chain of F maps. So we're F mapping over a bunch of functors. If the first functor is a nothing, then every subsequent map will always return a nothing, right? And so we immediately sort of short circuit out of the computation, which is very useful. But when we're doing something like parsing, especially in the situation of the C addresses, where if we fail on parsing the initial destination, we actually don't know if we've really failed because we want to check for the computation. And so even though the first one will return perhaps a validation error, we still want to give it the chance to succeed on only a computation. But then when we succeed on the computation, we can't just continue assuming success. So we need to continue parsing the end of the line to see if there is then going to be a valid jump. And so we want to be able to have like an fmap-like experience, but we don't want to immediately drop out as soon as something goes wrong. And we're going to demonstrate this. We'll show it. It's up to you when you write your instance of applicative of what is wrong, which is when we and how you chain these together. Okay, so let's actually go ahead and take a look at writing something. Okay, so I've got a little file here. A very common, like you'll see lots of examples like this when you start looking into this, but a very common way to teach and use applicative is through looking at validation. And so here, on line 6, I have a validator type. And this is going to be a sum type with two options. It's going to be a warning of A, which is my sort of like something went wrong, or it's going to be a report of B, which is like something went right. And then just for ease of teaching this, we're going to be looking at dealing with numbers, ints in particular, and a very simple validation case, which is numbers that are too big or too small. And so the first thing that we're going to have to do is we're going to have to make an instance of functor, right? And so I've got this right here that we have fmap, and it's undefined. We need to implement it. Okay, so y'all already went through fmap and functor, right? So I'm going to want some help writing this one, but I'll do some more of the heavy lifting once we get into applicative and alternative. But with functor, y'all should be able to help. So what's the first argument that fmap is going to get? Function. Perfect. And what's the second one?
The validator?
Yeah. And yeah, are we going to do this?
No.
No.
We'll match on the value constructors. So
Yeah. So we're going to have like a report of X, and we're going to do like a warning of X, something like that, right? And so what do we know about, like, this is pretty much the same as the either, right? And so what do we do in the case of the warning? We just have to return it, right? Because it comes first, it's part of the functor structure. We can't, if we start changing it, then we'll break the laws of composition. So we can't do anything. So the only interesting stuff is going to happen with here. And so what do we do here? Report f of x. Does that look pretty good? Let's see if looks pretty good to me. So now if we have a report, let's say we do fmap. Probably don't need that. Whoops. I do. I started down that line, but then, okay, so that looks pretty good. And what happens if I do a warning of just like we'd expect, right? So let's go ahead and take a look at this applicative. So the first thing that I'm not sure if we've seen yet in this week is that we're actually putting a constraint on the polymorphic type of applicative. And so we're saying here, we're making an instance of applicative for validator A, where A is anything that has an instance of a monoid. And the reason for this is that we're going to want to, as we map through or map over our validators, we're going to want to be able to accumulate all the ones that went wrong before. And anytime you hear like accumulate, you should probably think append, concatenation. And anytime you hear those words, you should think monoid. And so we're going to do that. So we've got here first, the pure we know is just going to wrap up whatever value we have into an applicative. And so what we're going to do is we're just going to actually basically alias pure to report, because it doesn't make sense for us, unless we're extremely cynical, to wrap it up in the yeah. As a front-end developer, I'm pretty close to that cynical, but I'm not there yet. So now we have our spaceship operator, or apply, and we're going to want to go ahead and take a look at implementing this. And so this can go a few different ways. So we're going to want to handle here. I'm actually going to remove this. So in the case that there's one case where they're both successful, right? And there's one case where one of them is successful and the other one is not. There's a case where that's flip-flopped. And there's a case where they're both unsuccessful.
We're not going to use the parents here?
What?
You don't need parents with operators. No, like
Oh.
around report X.
I think we're okay, since that we have the infix operator.
Yeah. The stuff in the middle is an operator, so Haskell knows that the stuff on the left-hand side and the right-hand side. With the implied parentheses.
We start running into, you can, if you do :I on the different operators, you can see what their order precedence is.
Right, that's
And this is something that I never remember, which is why I made the mistake before. So I just kind of wait for the red squiggly lines and add the parentheses as necessary. But here we're going to be okay. But good check, and please keep keeping me honest. Okay, so for this, let's handle the case where everything goes well first. So this is going to be very similar to our functor. Yeah, x and y. I'm gonna make this an f to make that a little bit more obvious that it's a function. So here, given an applicative explicitly with a function in it, and another applicative could have a function, could have a value, but it needs to be a value that can be applied to the function that is held by the initial applicative. We're simply going to return a new applicative report where the function has been applied. So now, if we take a look at these two, we're going to want to, in this case, actually just go ahead and return the warning, right? And so in this case, we can kind of ignore what the other one was. Since we're ignoring what the other one was, we can kind of see that handling this next case is also not super useful. And since we're actually going to handle this case on its own, you might wonder, what are we going to do here, right?
You still need the other case, otherwise your pattern matching will not be complete. Right?
Good point.
Or you just remove report. You can understand.
The whole thing? Sweet.
No, you cannot do that because you
Oh, yeah.
assume you're going to use the monoid instance to collect the errors, right?
Yep. This is where our testing would save us, right? Okay, so we're good. If the warning comes first, we'll catch it. If the previous one was successful, but the current one is not, then we'll catch it. Otherwise, we're going to go ahead and use the monoid to return a new warning, and we're going to concat them. Does that look good? Cool.
Wouldn't semi-group be enough here?
Semi-group would be enough, but since we have an applicative with a pure, we are also required to have instances already of functor and monoid. And so I'm not sure if it's actually just convention to reference the monoid concat if you have it, but I think it would make sense to, since we already have to have an empty element basically for our concat, just to use the monoid and not drop to the semigroup, which doesn't have also guarantee the empty element. I think because this probably gives us some guarantees as we're folding. Does that sound pretty reasonable to anybody else in the crowd? Okay, getting a couple head nods.
Yeah, it's like this data type looks quite similar to validation that's available in Haskell already.
This is basically the same thing. Yeah, we're just sort of walking through it in attempt to really make clear what's happening. And I think that sometimes even just like seeing each line typed out, well, first helps catch things that I'm maybe doing a little bit incorrectly or gloss over things that I've missed. And it also just keeps us focused on like each thing instead of seeing what's going before. So let's go ahead and take a look at some examples here. And so if we take now our same function, we can actually take our same function and we can toss that into a report. So we can do something like let f equal report, and let's give it a function, and boom. So we've got f, and f is a validator that has an A1 to A2 in it. So we're looking pretty good. And so then we're going to go ahead and make a second one. If we say and now we can go ahead and test out our combination. And we get the addition that is held in the first validator applied to the 5 that is held in the second validator, which returns a new validator that holds the value 6. But if we do the same thing, and we say let h equal warning, then we try to map our function over that. Instead of getting like some kind of nasty error of saying like, oh, you're trying to add a string or whatever, we get our error. And if we map multiple ones over, we can get multiple ones, right? And so, and in this way, you can kind of start to see how you could like start running through some text, and you could collect errors whenever they pop up. And at the end, you could give all your errors to your user to say, not just this was the first one that went wrong, but these are all the ones that went wrong, right? And in some cases, like that's not what we want, right? We'd rather have something that would short circuit, but this gets us a little bit closer to what we're going to need to do to actually parse stuff. So now we have the alternative. And so the alternative is going to require us to give two things. One is an empty, and the second is this this other infix operator, which I actually don't know what the words are for this one, if anybody does. But we can just say applicative operator. But so we go ahead and we're going to say our empty case is just going to be a, in this case, the bad scenario, the warning with an empty, because that's what we're going to want to end up with if we never have a success, right? And so in the other paradigm, we're always kind of assuming success, and if we get a failure, we start accumulating them, or assuming success, and if we get a failure, just short-circuiting, returning that failure. But in this case, since we're going to keep trying, we need to have our last case be assuming that we tried all the options and none of them worked. And so we're just going to give a warning with an empty. So then we're going to go ahead and start defining this case. And so we're going to do first happy, and since we're going to say, hey, if we found what we're looking for, then that's great. Go ahead and return it. And then we're going to say, if we found, actually, let's do this. If we found what we're looking for and anything, and a report, then that's great. Because we really don't care. We're just looking for one success. And then if we find a report and a warning, then we also don't care, right? Because we found something that worked. And then if we get a warning first and a report second, we're also fine. And then the final instance is warning and a last warning. And then we're going to, actually, do we want the first or the second? Oh, we need both. This is why we need a monoid here as well. And this will be warning Is that looking pretty good? All right. So let's go ahead and take this for a spin. So if we have, let's store, go away. A is going to be validator 5. Okay, actually we can.
It's got to be report type then, right?
Yeah. And we're actually going to use, just to kind of show how this might work in the context of a function, we're going to use this little validate number helper function that I have. So this takes in a number. If the number is less than 50, then it says it's too small. If the number is greater than 100, it's too big. Otherwise, it's fine. It's just right. And we're going to return the report. So here, we're going to validate. We're going to do validate number. And let's pass in 32 just to see what it gives us. Okay. And then let's validate number like 101 just to see what it gives us. Pretty good. So what do y'all think is going to happen, oops, if we do this? Oops. What's going to be the result? So take a look at here. So the first one is going to return a warning with a list of too small, a list with a single element too small. The second one is going to return a warning with a single element that's too big. So if we use this applicative operator, what's it going to be? I think we get a list of all the errors that occurred. What happens now if I put one of them in the safe zone? So we don't get the too small because this is one of the big differences is that we're basically starting out, and as soon as we hit something that we like, we actually assume success, which is really going to be important for when we're parsing the line where there are different options, right? Because if there can be 3, then we need to look at the first one, and if the first one fails, it's not a real failure yet, because we can still have a valid instruction. Then if the second one succeeds, we can still have, we're looking good, but we could still fail if the last one was completely like messy, right? And so we need to have a distinction between what's okay to keep moving on and trying to find a right, correct syntax without failing. And so in this case, we're just using this one, which I think a good way to think about it, the people say is choice. Saying like a valid number here or a valid number over there, it's okay. I'm giving the program 2 branches to take a look at and try. And if that one tries, then it's good, and it's going to keep trying and trying and trying. So we get the right 55.
So what happens if the first 2, no, let me think about that.
So
The first 2 fail and the last one is right.
if the first 2 fail and the last one's right, then it's going to be okay. We're good.
But in your system, wasn't it so that the middle one was actually...
Yeah, there's some more operators that are going to help us out. And we won't have time to go into every single operator, but what I'd recommend is that you go ahead and first take a look at the applicative type class, and then take a look at the parsec documentation. And I'm also including at the end of these slides a few articles that were extremely helpful to me in figuring this stuff out. But these kinds of situations were the ones that really got me confused. And I was like, well, and also this is one of a lot of times people, when you're learning Haskell, they give you they say that you get so much of an assurance when it compiles, right? If it compiles, it almost always works.
Not the old one.
But when this is the almost, because all of these parsers are kind of just looking at strings and returning another string. And so there were lots of circumstances where I got a valid output, it was a string, and I had a valid input. It was a string, but it wasn't quite exactly the string that I wanted. And so, but there are several operators that can help us out. Okay, so I think with this, we're probably in a decent place to start jumping into my project. Okay. Okay, so let's see. I actually did some refactoring on this last night. And I think this is, yeah. And it was amazing. Yeah. So I think I got home, it was like 11 o'clock at night when I got back to the hotel. I'd had a couple beers. I got up that morning at 4 a.m. because I'm completely jet lagged. And so these are basically the worst, just about the worst circumstances to be programming on, right? Like if there was a time where I couldn't trust myself as a programmer, it was probably that point, right? And so I'll show you what I changed. I still have this comment here, or I can even show I think I have a pull request. Updated 17 hours ago. You do the math. Yeah, so I basically, so at the time that I wrote this, I had never heard of like the BNF grammar notation, and this isn't quite BNF grammar notation still. And I'd actually like help with that if anybody, here, I'll make this bigger, I think. And I also had a much less firm grasp on data constructors and new types. And so I knew that I wanted to basically have a data type for my instructions. That would be like, these are all the instructions. And then I wanted to have particulars so that I could say, I'm going to parse a C instruction. And then I knew that the C instruction needed to have jump, destination, and computation. What I'd done previously, which I decided I didn't like as much, was I had this data, which was like its own kind of like C part data, and it was a sum type of these things. It could be a destination, a computation, or a jump. And then here in the instruction, I had C, C part, C part, C part. And just, it felt like really clumsy to me, and at the time that I read it, I just had no idea. And I was also just mainly excited that Parsec was working, so it's kind of like, woo, run away. But last night I was like, I'm going to show this to people. I should try to clean up my house a little bit. And so I refactored it out of this data sum type into new types. And this made it pretty nice because I have, I still have the atomic semantic meaning of each of these types, but they don't need to be wrapped in the data type constructor that doesn't have any semantic meaning to me. And you could tell because C part was kind of showing that I was at a grasp for a way to describe this. And then it also makes the data constructor of instruction just read really the way that I was thinking about the syntax or the grammar in my head, right? That C is either a destination or a computation or a jump. It's not a C part or a C part or a C part. That doesn't give me very much. You know, I have to look in two places and whatever. But changing that affects everything, right? It touches the parsec types. It touches my evaluation types. It touches, you know, like pretty much everything. This isn't a giant project, but it really was, I can attest, it was the thing. Like make the change and then just start following the compiler errors. And they really do just lead you down the path even if you're hungover as hell and a little bit drunk. So if that can't sell it to your manager, then I don't know what can. Okay, so here's our syntax. I think that that's going to be good. Let me make sure this is still. Wait. Always helps if you build the right project. Not even a compiler can save you from that. Okay, so we've kind of walked through this, and this basically just gives us a nice, tidy data type for our syntax of our little simple thing. So now we're going to jump straight now to the parser part. And so you can see here my module is assembler parser, and I'm exposing the run parse function. And so I don't want the other parts of my application to be messing individually with these things. I just want to be able to run the parser. So let's take a look at this. On line 44, we have, actually let's do parse. Let's do parse symbol. Now, we'll do parse address. Okay, and I'm going to briefly kind of talk about what some of these additional operators do, but to look more in depth of them, check out the docs. So parse address on line 44. Each of these parsers is going to have a type of parser, which comes from parsec, and then it's going to have the data type that we want to parse to. And so the instruction encapsulates the data type of all of my options. So most of these are parsers to instruction. And then we have here car. You can see the type of car here. It's a function that takes a car and a parsec t of string, a unit. We have an identity, and then finally a car. And so that's a pretty intimidating type signature. But you can kind of just give yourself a little bit of a shortcut and just say that basically all of these matchers that are coming from parsec are really, like, as long as you have the type signature wired up for the function correctly, where it's a parser and the end data type that you've defined, which is super simple, right? It's just whatever you wrote over here. As long as that's wired up completely, then whatever the matcher follows is just going to be the text that you wanted to match. And so car looks for a character, and the character that we're going to look for is the @ character. And we know that every single address instruction always starts with an @ character. So this is just saying that if the first character is an @, then there's a good chance that this is a address instruction. And so then this little operator here is similar to bind, but instead of binding and grabbing the value out, it's going to bind and throw the value away. And so when we actually turn this into machine code, if we already know it's an address, we don't need to also hold on to the fact that it started with an @ symbol. So we match and we throw it away. So then next, we use our choice operator, right? And so what we're saying is that since you've successfully matched on an address, this must be either a location or a symbol. And I really don't care which. So either of those can succeed. And so here I'm going to call parse location and parse symbol. And parse location we'll do first. And so this is a good one. We're on line 34 here. These parser combinators are not just applicatives, but they're also monadic. So we can use the do syntax with them. And so here we have do. And this is going to grab some kind of value and use bind to store it in L. And so many1 is going to say we're going to look for one or more digits. And we're going to bind that into 1. And here, this is definitely some spot where we could do some assurances, try to say, if it's a location, then we actually need to make sure that there's only 16 numbers, right? So this is definitely a naive implementation, but it also works. So, and then finally, when we return, this could also be pure. the return is just aliased to be pure in the actual source instance, monadic instance. So we can use either return or pure, they're identical. And we return a location of L. And now remember that it's very important that this function does not return a location L, right? It wraps up location L into a parser combinator. And so the end result of this is going to be not a location, but it's going to be location inside the parser combinator. And the reason why this is important is because we need to not just stop here, but we need to combine these with the whole thing, right? We can't just match one thing, we've got to match everything. So,
Many1 and the digit, is that stuff that comes from the...
uh-huh. Many1 comes from parsec, digit comes from parsec, and you can check out all these matchers. It's just really, like, it's one of these things that it's quite hard, in my opinion, to keep the whole thing in your head about how all this is working. But the API is designed in such a way that you really don't have to. And so if you can keep in your mind like how the choice operator works and the bind and the bind that throws away the thing, and then you can use this quite well, quite effectively, without having to keep in your head the entire sort of recursive thing that's going on. Yeah, so car comes from that, many comes from that, spaces comes from that. So you can just look for, that's how I'm kind of checking for, like, I noticed that some of the source code that I was working was indented funny. So I'm just saying, like, you know what, if it starts with white space, I don't care about it. At any rate, so then we have another important one here. Let's take a look at this. Well, yeah, let's talk through the computation, destination, and jump. So here, this parse instruction is actually where we're going to try to parse the entire C instruction, right? And so what we do here is at this point, we're assuming that we've got something that very well could be a C instruction, and it could have a destination, a computation. It could have a destination, it must have a computation, and it could have a jump. And so here, we're going to do a try to parse destination, which there may be better ways of doing this. And so I'm very interested if folks out there have some answers. But I needed a way to not straight up fail, but say that, hey, since this thing is completely optional, let's try to parse the destination. Yep.
There's an optional combinator.
Cool.
We call optional.
Cool. I tried using that one at the time I wrote this, and I couldn't quite get it to work. But I'll give it another try tonight, and I'm gonna bug you if I can't. So basically, and it probably does something pretty similar to this. So the try basically says we're going to force it into the other option if this fails. And so this is kind of ensuring that if I don't have a destination, I am going to begin with a destination of empty string. And at the end of this situation, I'm sort of saying that I always have a destination, and this probably had to do with the way that my my data structure is set up, right? Because destination doesn't take like a maybe or an either. It just takes a string. And so I'm kind of like forcing it, saying like, hey, even if this fails, you're going to succeed by returning, wrapping up a new applicative with the destination of empty string. Then we parse the computation. And then here, we parse jump or return an empty jump, and we wrap that back up. At this point, we're pretty close to being able to do what we want. Parse symbol over here, notable one of matcher, where you can give it a certain allowed symbols, do your kind of like little custom matcher. And the other thing that is cool about this is so that actually at the time that I wrote this was for just the local Utah Haskell meetup, and I was doing a little thing, and I was trying to run the exercise that we're going to do at the very end of this, and I had assembled pretty small programs, and they had worked out, and I wanted to assemble something more dramatic, and I ran through the program, and it ran, and then I loaded in the machine code to my emulator, and it didn't work. And I was like, oh no, what's happening? And then so I started running through it, and I figured out what was going on was that I didn't realize that this $sign was legal for symbols as well. And I was thinking at the time, it was probably like 2 minutes before the thing started, and what it would have felt like if at that point I had needed to take the regex that I had written over the course of the last, couple weeks and insert like an additional character into this one spot and be sure that it wouldn't break the whole rest of the thing, or that if I even could still read my regex at that point, right, it would have been pretty scary. But since each of these are atomically separated, where this is a parser for an instruction, I have a pretty good assurance that by altering this parser, I'm not going to have too far of consequences outside of the scope of this operation. And it was pretty trivial just to say like, oh yeah, I was matching for those and I'm just going to put that in. It's really match for one of those two versus match for one of these three. Like, it was really nice, and it just worked, which is going to make the next part really embarrassing if it doesn't. But what we're going to do is we're going to go ahead and build up this pup, and then we're going to take a look. There's some other stuff in here that I'm happy to go over if y'all are interested, but like what I need to do before the parsing, I needed to actually create the predefined symbols map of symbol to memory address. And then every time in the evaluation, when I come across a symbol, I need to look it up in the map, and if it's there, get the address that it already has, or if it's not there, assign it to a new address with the value of the previous memory address in binary +1. And so there's some other stuff, but it's not strictly related to the parsing, but just some fun stuff. So basically what we're going to do in our I/O, we're going to read in our text and grab that in contents. And processing the text includes parsing the lines of the text, building the map of predefined symbols, then folding over the predefined symbols map with also a -1 to indicate that the first time that we increment address, we're going to be at 0 with the currently parsed lines. And then we are going to have, at that point, we're going to take the instructions and the symbols, and we're going to fold all of those into a function getMemoryLocation that is going to do the work of saying, like, are you a symbol? If you're a symbol, do you have an address? If you have an address, use it. If you don't have an address, use the next one. And then finally, write it back into the file in the machine directory pong.hack. And so we're going to I'm going to go ahead and just YOLO. We'll move it to trash. We won't delete it completely. We're not insane. So we're going to take this file, thousands and thousands of lines long. It's not, Microsoft Windows, but it's around 30K lines long. We're going to show you, we're going to run the executable that was just built. Hey, that was pretty fast. We're going to go ahead, and I've got this running right here. Let's go ahead and here, we'll run this one first. So this is the, let's go ahead and I think we want, I know there's a way to clear this. Here, I'm just actually going to delete and close. Okay, so we're going to start out with a simple one, and then we'll save the wow for the last. So here we've got the same little program that we looked at before. And so when I loaded it, I loaded up the machine code. So it looked like this. But over here, we can see that the simulator has interpreted it correctly, right? So I already have a pretty good feeling that, that this is going to work. And what this is going to do is going to take the contents of register 2 and the contents of register 1, and it's pretty cool. As this goes, you can see it, like which register it's taking a look at and how it's executing. And finally, oh, I did it wrong. It's going to take the contents of, this means that I probably explained this a little bit incorrectly in the very beginning of the lecture too, which is why we write code in Haskell and not assembly. Let me be a warning to your children. So it looked at 150, and then it stored 100 here because it was bigger. If we change this one to 20 and this one to 75, it'll look at both of those. And store 75 in the third. One thing that's interesting is that for safety reasons, not security reasons, throwback, this line 15 you see is 0 jump. It's 0 because we have to have a computation, and it's jump because we must jump. If we don't end each of our applications with an endless loop, that will allow our CPU to be hijacked and for people to insert commands into the spots as the CPU is running through. Like if it just keeps running, then somebody else can come in here and put some arbitrary code to execute, right? So I thought that was kind of a fun thing learned. Okay, so now for the big finale, the moment we've all been waiting here. Here's the Pong that we just knew. I'm going to take this animation off because it takes like 9 million. The Haskell is fast, the simulator is not. We're going to run. Boom. And you didn't know this, but now you all have to sit here till I die. It was part of the contract. I told Michał, I'll only do it if they have to watch me. Just kidding. Yeah. Okay, so that's pretty much all I have, but I do want to say a couple things. So first off, I just think this stuff is just so dang cool, and I'm learning a ton every day, and this was a big milestone for me, getting this parser to work, and it felt really like pretty close to impossible when I started, and I had lots of false starts, and I had some moments where I wasn't quite sure it was going to get to work, and if it wasn't for the help of the local Haskell community in Utah, I wouldn't have probably gotten through it. And so sometimes people, when they're talking about functional programming, they say things like, oh, it's just so simple to reason about, and it makes blah, 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 and everything's easy. And the reality is, at least for me, and I think for many of us, it's hard, right? It's hard, but it's worth it. And I think it's okay to acknowledge that. And it's okay to reach out to your friends and your community and help build your community. And also, when you don't know stuff, let people know that you didn't know it. Because the more that we're honest with each other about how we're all learning, the more it makes it approachable, that we can all say like, hey, look, we're all in this together, and we're sharing our knowledge, and we're not trying to hide what puff ourselves up into things we're not, and that way we grow together. And the final thing is that this is my my last little presentation at the conference, and it's just been like an incredible experience to come out here to Poland, and I couldn't thank the organizers and all of you so much for dedicating your time to listen to me talk. And if you enjoyed it, I would ask that you do two things. The first thing is that you commit to taking a look at Haskell book or the course Nanta Tetris, or both. I think they really, each of those resources really changed the way that I think about computing and about programming, and made me a better programmer. And I would like to encourage you to do the same. The second is to, if you're excited about this stuff, share it with somebody at work, share it with somebody at the home, do a presentation at your local meetup. I hope that seeing that, that I'm not some crazy wizard and doing this stuff and proposing to speak here helped get me to Poland, and to meet all of you, right? And so, like, really amazing things can open up if you stick with this stuff and you put yourself out there and you're honest. So thank you so much for all you do, and let's go have a drink.